Swayam Prabha. Digital India. Educated India.
So, hello everyone. So, we will continue with the isotropic membrane. So, second type of membrane is track etched membrane. So, here you can see this type of membrane is prepared by actually irradiating a polymer film with charged particle. So, you have a polymer film. So, if I see from the top view, this is the polymer film, the charged particles are actually they attack the polymer chain. So, polymer chain is there. So, charged particles are projected on the film, polymer film, and that will actually attack the polymer chain, and which will damage the molecules, and this damaged portion will create the pores. So, that is the process of track etched membrane. So, this film is then passed through the etching solution. So, where the damaged portion will get removed and the damaged molecule dissolved to produce cylindrical pores. So, you can see here whatever if the particle it is there, the charged particle is there, and this is a film, and this portion the polymer will get damaged. And when we pass this treated, the charged particle treated film with the damaged portion, with the etching solution is there, and then this damaged molecule will get dissolved to produce cylindrical pores. So, effectively what we will find, we may find this type of pores if the charged particle comes in vertical direction or maybe at different any angle we can create. Many of which are perpendicular to the membrane surface. So, most of them are perpendicular. So, but here we can create an isotropic membrane. This is one of the isotropic membrane manufacturing process. So, you can see this is the here a charged particle actually damage the pores, okay, and here this portion can be etched out and leaving the this pores here on the polymeric membrane. Next is the expanded film membrane. So, this is another method of manufacturing the isotropic membrane. These are oriented crystal polymers with voids created by extrusion and stretching process. So, there is a polymer extruded. So, this is a polymer extruded and form the film, and the film is getting stretched, and when we stretch the polymer, okay, we create the voids, crack we create. So, in a polymer after stretching we can create the micro cracks by stretching it. So, if it is done in controlled fashion, we can create the isotropic membrane. So, first the material is extruded near the its melting point temperature, and then it rapidly drawn. Okay. So, at this is the V 2 V 1. So, V 2 is more than V 1. So, this is stretched rapidly drawn. So, it is a rapidly drawdown rate. So, at very high speed we can draw it. The extruded material is then cooled, annealed, and then stretched up to 300% to its original length. So, here it is a before we stretch we cool down it and then annealed to set the polymer film, and after that we stretch it maybe up to 300% of its original length. During this stretching the cracks are created. So, this stretching process creates slit like pores. So, and its size may be from 0.02 to 0.25 microns. So, we create a slit like pores. So, this type of pore, this is the ACM image. Okay. So, expanded film membrane. So, here we can see the micro pores are created due to the stretch. The crack, these are the crack formation you can see. And apart from the isotropic membranes, there are anisotropic membranes as I have mentioned. So, one is the phase separation membranes. These are homogeneous in chemical composition, but not in structure. So, that is important. We want actually the structure, we are creating the membrane structure, not the chemical. Chemical may be same, polymer may be same, but we are creating the anisotropic structure. These are produced via phase inversion technique. This is the technique, phase inversion. The pore size and porosity vary across the membrane thickness. So, that is the important. In anisotropic membrane, the pore size and pores are maintained, it does not vary, but here across the membrane the pore size and porosity varies. So, it often consists of rather dense layer of polymer on the surface and increasing porosity. So, that is so porosity actually is increasing. So, first a dense layer of polymer and on the surface. So, the porosity varies. So, here it is a dense layer at the bottom. So, with the low porosity, very low porosity, and here we can use with the higher porosity. So, in this process we can create the gradient porous structure. Initially there will be higher pore size and gradually the pore size is reducing. So, gradient filtration is there. So, here we can see this is the type of structure, phase separation membrane. So, it is used by phase inverse technique is used. Next is the thin film composite membrane, where multilayer composites are created, and they are both chemically and structurally heterogeneous. In earlier case we have seen it is from single polymer, single material. So, it is chemically they are homogeneous, but not structurally. Structurally they are inhomogeneous. So, but thin film composites are chemically and structurally heterogeneous, they are not homogeneous chemically. So, there may be different chemicals at different layer. So, this usually consists of highly porous substrate, okay, coated with a thin dense film of different polymer. So, first we have a particular polymer with highly porous structure, and then on that another layer of dense polymer is deposited with a very small pore size. So, here you can see the structurally they are heterogeneous and also chemically they are heterogeneous, because in one surface, one layer we have different polymer than other layer. So, that is we can create this type of anisotropic membrane. It is called thin film composite membrane. So, one thin film is created, dense film is created on a polymer substrate. This can be made via several methods, including interfacial polymerization, solution coating also there, plasma polymerization, and or by surface treatment. We can do surface treatment to change the chemical nature and physical nature of the polymer and create the heterogeneous structure. So, we can see this is the polymer here. So, here at the bottom we can see the bottom layer is having larger porous polymer, and the finely dense polymer is deposited on this substrate. So, isotropic and anisotropic membrane refer to flat sheet configuration. So, they are actually these membranes are basically they are basically in a flat sheet form, but we can till now whatever we have discussed, all the membranes are of flat sheet form, but we can also produce like a hollow fiber, hollow cylinder in this form, where the water can penetrate through the core and they can get discharge from outside or vice versa. Typically what is done here is the water with impurities can come from the surface and then clean water can go out. So, this type of membranes in cylindrical form can be created, that is the hollow fiber membrane. Like flat sheet, these fibers can either be isotropic or anisotropic. So, we can create from the flat sheet they also can be dense or porous. So, that we can create depending on our need. Common fibers used in the industry today are anisotropic with a denser outer layer around a porous tube. So, that is a basically very commonly used here. This is a tube here, denser outer layer. So, outer layer is denser, okay, and then inner layer, this inner layer is porous. This type of anisotropic can be created, and where water can penetrate through the core and then clean water can come outside. So, this type of system can be generated. So, the one advantage of hollow fiber membrane is that they have more surface per unit volume than the sheet form. So, that we can create the higher surface. So, pressure drops will be not that high, the discharge, the water, typically large volume of water can be done, what that is filtered out. We see this is the type of hollow cylinder can be produced here, where inside you can see that it is a porous here and covered with a relatively compact. Okay. So, the anisotropy is here also in the thickness. So, it is a mix of the fine pore and the open structure. So, there are different types of materials used to create the membrane, and they are basically synthetic organic polymers. So, most microfilter, ultrafilter or reverse osmosis nanofiltered membranes are synthetic polymer membranes, organic polymers, and typically microfilter and ultrafilters. In case of these two filter, we use different types of polymers like polyvinylidene fluoride, polysulfone, polyacrylonitrile, okay, and different types of copolymers we can use. And for ultrafiltration, its most commonly used polymer is polyether sulfone. So, this polymers are used. Basically, typically we should take precaution to select the this type of polymer. Just its lifespan we have to create. It should not be reactive with the water. So, all different types of precaution we have to take. And for microfiltered membranes, so also we can use the cellulose acetate, okay, and cellulose nitrate blend we can use. We can use nylon, different types of nylon we can use. So, PTFE polytetrafluoroethane we can use for microfilter. So, PTFE membrane is very commonly used for microfilter membranes. For RO membrane, membrane typically, so for RO we use typically the cellulose acetate membrane or polysulfone coated aromatic polyamides. So, for different types of membrane we use different types of materials, different types of polymers. For nanofilter membrane they are made of cellulose acetate blends or polyamide composites like the RO membrane. So, all these materials are very commonly used for different types of membranes, or they could be modified form of ultrafilter membrane such as sulfonated polysulfone. So, all these materials we can select to produce all these membranes. So, apart from this organic polymer, we can also use inorganic materials such as ceramics or metals to produce all these membranes, different membranes. But the problem of ceramics and membranes, they are not that flexible. So, ceramics membranes are microporous, thermally stable, they are chemical resistant, and they are often used for microfiltration. So, this due to the thermal resistant and chemical resistant. So, ceramic materials are used. The main disadvantage of this inorganic membranes are their high cost. Cost is very high and they are fragile, mechanically they are fragile. So, that is a problem and have hindered their widespread use. So, due to their fragileness, so we cannot use we cannot change the shape, they are not we cannot use widely. So, for a very specific application we can use the inorganic materials like ceramics. Okay. And metal membranes are also used. So, they are used made from stainless steel, and we can make very porous membrane. So, they are basically this inorganic material like ceramic and metal membranes are basically used for gas separation, high temperature gas separation we can use, but they also we can use in water filtration like high temperature water filtration or as a membrane support. So, that is for a membrane we need a porous support, and in polymeric membrane at high temperature we cannot use. So, high temperature filtration, even a liquid filtration we have to use this inorganic ceramic or metal. And for polymeric membrane, as we have already discussed, organic membrane, we need some stable support. For that support, some porous support we need. So, for that this inorganic, the ceramic or metal membranes are also used to provide the support on that. Now, we will discuss that okay, we have discussed different types of membranes and different types of polymeric material, different types of materials, but membrane will only work if we can place the membrane in correct position. So, a membrane will not be able to work filter out the pollutants, the contaminants. Membrane is created, but membrane has to be placed properly in a place, in a frame, so that the water can, we should allow the water to pass through from one side and water gets cleaned. Okay. Suppose this is a frame, we want the water to be cleaned, this is a membrane, okay, and here we are allowing the contaminated water and it is getting filtered out and clean water, this is contaminated and ultimately we are getting the clean water and this is the membrane. Here this is a, sorry, here is a, it is a membrane. Okay. Now, this membrane we can, how will you put? For that we need one mold. So, there are different types of molds where we can actually set, we can place the membrane, we can in a proper position, so that proper location, so that the water can be filtered out or any liquid can be filtered out. So, this is called molds for the membrane, and there are different types of molds depending on our requirement and depending on the type of membrane we decide the molds. The each and every mold, different mold, they work in different, with the different principles they follow. So, there are typically 4 main types of molds. One is plate and frame type mold. The plate and frame type mold is the simplest configuration. It consisting of 2 end plates and where the membranes are placed in flat mode. Flat membranes are placed with some space, at different space we can place the membranes. It is called plate and frame mold. So, plate and frame, this is the simplest one, and where we place the membrane in the flat form. So, this is the plate and frame type of configuration. Here if we see, this is the filter medium, that is actually also our membrane which we are talking, this is the membrane, okay. And here it is a plate, this is a plate through which, this is a plate through which the slurry will penetrate, okay. Slurry will penetrate through this and slurry is penetrating, and here there is a frame, these are the frames, okay. Now, you can see here in this slurry is penetrating through the frame here in this zone, slurry is penetrating where the frame is there, and then this frame is actually holding this filter media, that membrane. and here when slurry is entering and it moves in both the directions, because the filter medias are, the membranes are placed with certain space. So, as the slurry, that is water along with the other compound, other particles enter, and then due to the pressure drop it flows through the membrane, and on the other side, this is this side you can see, I will color with the red, this side we are getting the clean water, and clean water is coming out through in between the this frame, through the plate, you will get the clean waters are coming. Okay. So, you can see the plate portion, through that clean water is coming and it is collected, and in between the frame, if you see within the frame here, the particles are collected here. We can collect the particle within the frame and then we can wash it and then reuse it. The frame is here, okay, is kept between the plate, and there the slurry is that is cleaned and clean fluid is collected from the other side, and then if we want to replace, so we can replace this frame, the filter media, that is membrane, and we can fix it on the frame. So, plate and frame filter press, this is the diagram. So, frame is basically made of carbon steel. So, these are the frames, carbon steel, and plate and frame metal. So, the plate is PP filter plate, and filtration medium, any filter cloth or maybe membrane we can use. And the filtration precision with this mesh, it is 1 to 100 micron. With that zone mainly used for coarse filter. Main application of this type of frame and plate filter is that food, oil industry, slurry, mine industry and chemical industry. So, we will continue with this molds for membrane. The other type of molds is that tubular mold. So, the membrane is often on the inside, which we keep the membrane inside the tube. So, if it is a tube, okay, in the tubular form, so this is the mold, okay, frame, and here we are actually keeping inside, the membranes are kept in the inside the tube. Okay. So, it is inside the tube and the fed the solution is pumped, the feed solution is pumped through the tube through. So, here this is the way we do filtration. So, the through the core center, that is inside, we pump the feed solution with the contaminants and the water or some fluid, clean fluid comes to the surface outside. So, this is the typically tubular membrane. Also we can have at the outside also, outside of the frame mold. So, this is the typical tubular mold. So, here we can see the one is where the solution is fed. So, the raw water inlet, here it is a raw water inlet, water with all the contaminants, it enters them, and here you can see that the membrane is kept inside the frame. One is raw water inlet here, the next is the tube. This is a tube, okay, and in this tube the exit outlet is also fitted, and this is the tube here, and membrane support material. 3 is the membrane support. Here there is a support material for membrane which supports the membrane, and then the outlet, 4 is the outlet, the whatever the permeate that comes out, it comes out through this channel 4. Then the 5 here it is a, this is the membrane, actual membrane here. So, membrane frame is here and this is the membrane. And from below the tube, the whatever concentrate which comes out, for normally for say in food industry, we want to extract the food item, concentrate food item. So, in that case also we can use this type of material, the concentrate material which is this is actually required material. But also in case of say water filtration, we take the collect the water, clean water, and here it is a whatever contaminants are there collected, that is outlet is there. And here you can see the in the water the particles are there in the suspension. This particle has to be removed from water. Now, next mold is the spiral wound mold. So, on a tube the membranes are wound spirally, that is the spiral wound mold. This mold actually the most popular mold in the industry, because it is a easy to wrap the membrane on a frame. So, for nanofiltration or RO membranes. So, for reverse osmosis or nanofiltration, in the industry we normally prefer this spiral wound mold. So, this is the spiral wound mold. Here you can see this is the frame here, and this outer casing, but in between we can see here the core tube is there, core tube, and through the core tube, over the core tube we wrap the membrane. So, there are different layers we can wrap. So, feed water carrier, then semi permeable membrane we can use, and permeate carrier material. Okay. So, there it is wrapped, and the feed solution along with the contaminants, the water is forced inside, and the concentrate and permeate, they are collected after the filtration process. So, this mold has a flat membrane wrapped around the perforated permeate collection tube. Okay. So, this is a perforated tube. The feed flows on one side of the membrane, and then through membrane it is actually the filtration takes place, and permeate is collected in other side, on the other side of the membrane, and spiral in towards the center of the collection tube. So, this as it is the water is, it is a wrapped. So, the permeate is actually spiraled around that, and from outside it goes towards the center, and where the permeates are collected through the center, and during its path the concentrates are actually filtered and then they are collected. Next system is hollow fiber mold. Here, so here we can use this type of mold for removing the salt, desalination of sea water. So, it consists of bundle of hollow fibers in a pressure vessel. So, the fibers, hollow fibers are arranged in a pressure vessel. So, they can have cell side feed or other side. So, cell side feed configuration, whereas the feed pass along the outside of the fiber and exit in the fiber end. So, if you see the this is the fibers are there. So, the cell side feed is that the solution, that is contaminated water, will be fed through the cell side, and the after filtration the water will be collected at the fiber end side. So, this can also be used in bore side feed also. So, we can also in the, this is a bore side also we can feed, and the permeates are collected from the surface, where feed is circulated through the fiber. So, here the feed is circulated through the fiber towards the outside. So, both the systems are in use. So, you can see the diagram here. this diagram clearly says that this is the shell where at the center it is a bore site and here it is a shell site. If we feed the material through the bore site, then exit will be from the shell site or vice versa. If we can feed the material through the shell site, and then we can collect the filter water from the bore site. So, this is the these are the fibers, hollow fibers. Okay. Hollow fibers are arranged in this fashion. Okay. These are fibers. Now, these are the fibers here, and you can see these fibers are forming the filtration layer. Here this is the support layer, active layer, this is the active layer, you can see this is the active layer. So, this one is the active layer and the support layer is there. Now, if you see this diagram, the water with contaminants are there and they are pushed through the fibrous mass. So, here and this is the active layer here, and then the filtrate are collected. So, if you see here through the bore site, if we feed, then here it is a contaminated one, and with the high pressure we are feeding through the bore site, and with the pressure say PB 0, and ultimately the pressure will drop on the outside, okay, other side. So, in this way the filtration takes place, and this is called hollow fiber mold. Hollow fibers are used here, and this is employed for water treatment. For large scale water treatment plant, we use this type of mold. So, employed wastewater treatment and in membrane bioreactor. So, bundles of fibers can be suspended in the feed solution and the permeate is collected from one end of the fibers. So, that is the process of the hollow fiber mold. So, and now try to understand what are the different types of nanomaterials used for water filtration. So, nanomaterials have unique size dependent properties. So, when the size reduces for any material, so its surface energy changes, and in the nanomaterial main advantage is that high specific surface area. It has very high specific surface area. So, which actually makes it highly reactive, and it changes the characteristic, its high sorption characteristics, absorption it will be high, faster dissolution. So, that it changes the characteristics, okay, to the highest, and discontinuous properties are also there. So, if we change the size of the nanoparticles, nanomaterial, so we can change all the characteristics. So, this specific nano characteristics, so this specific nano based characteristics allow the development of novel high tech material. So, that we will discuss in detail in our experimentation. In our lab we have developed novel material based on nanotechnology. So, to have efficient water and wastewater treatment, that we can use. So, that in nanomaterial we can use nano membranes, adsorption material, nano catalysts, different types of functionalized surface coatings are there, surface materials are there, different types of reagents we can use using nanomaterial for water filtration. So, nanotechnology is widely used for water filtration. So, the types of nanomaterials which are used in wastewater treatment or water purification are, these are the different types of nanomaterials which are used widely. First is the nano adsorbent, we will discuss in detail. So, nano adsorbents, the main properties are, positive properties is that high specific surface area. So, it enhance the adsorption rate, higher adsorption rate. So, it actually nano adsorbents small footprint. So, carbon footprint is low. For making this we do not have that much energy loss, energy cost is low, but here the negative point is it is high cost of production. So, that is nano adsorbent. So, the applications you can see here, point of use, removal of organic, heavy metal, bacteria. So, all these applications we can use. Then nano metals and nanometal oxides. So, we can use nanomaterial in this form also. One is nano adsorbents, then nanometals and nanometal oxides. So, the positive point is that of nanometals or nanometal oxides are because interparticle diffusion distance is short here, compressible, abrasion resistance is high, magnetic properties are there, and it is a photocatalytic. So, if you see titanium dioxide, it is a nanometal oxides. So, titanium dioxide nanoparticles are used widely for water treatment, and the main drawback is its a reusability is less. Okay. So, by this nanometals we can remove the heavy metals like arsenic and some other metals. Okay. It is media filters, slurry reactors, okay, even powders, pellets, there are different applications are there. And third one is that using the nanomaterials, which is nano membranes we can use, and membrane composites, that we can use using nanomaterials. So, it is a membranes are reliable, largely automated process. So, we can produce the membranes, and negative point is the relatively high energy demand, because of the smaller pores we need pressure to pressure drop, higher energy to flow the fluid. So, this is widely used in all fields of water treatment, wastewater treatment, water purification. So, at present it is widely used this membrane type filters. Now, let us understand this in detail. So, nano adsorbents are basically carbon based nano adsorbents, like carbon nanotube CNTs are used. So, it is widely used in different materials, like high strength material we can use, even for water filtration we can use this. So, main advantage is that it is a highly sorption side is there. So, they are highly absorbent, and bacteria, it can kill the bacteria. This is reusable. So, nano adsorbents carbon based nanotubes we can reuse, okay. But the production cost is very high here, and main problem here is the nanoparticles, is that carbon nano, it is a health risk is there. If it mix with the water, if due to some nanoparticle, nanocarbon nanotube, if it mix with the water or if it penetrates inside the body, that will create a health risk. So, we should be very careful about this, and the main applications of carbon nanotube are heavily degradable contaminants. So, in those applications we can use carbon nanotube or carbon based nano adsorbents like pharmaceuticals, antibiotics. So, all these type of industries we can use this carbon based nano adsorbents. There are other type of nano adsorbents are there, polymeric nano adsorbents. So, what is that? So, bifunctional, like inner shell adsorbs organic and outer shell branch adsorb heavy metal. So, that suppose there is a nano adsorbent, there is a cell. So, the inner shell will adsorb the organic material and the heavy metals will be adsorbed by the outer shell. So, in this way we can the polymeric nano adsorbent we can use bifunctional. So, it is reusable. So, where we use two types of organic compounds like combined chitosan dendrimer nanostructure we can use. So, the bioadsorbent is biodegradable and it is a biocompatible and non-toxic. That is the advantage which we do not get from the other type of nano adsorbents. So, this is actually biocompatible, but the problem here is that the production process for polymeric nano adsorbent is complex and multi-stage. So, at first we have to create the core, then shell we have to create. So, this is complex process, and that is why this is not that simple, but this type of bifunctional nano adsorbents are used for multiple applications. The applications are removal of organic and heavy metal. So, if we see that in a water, the organic component and heavy metals are mixed. So, in those applications, in one go with using one material, we can remove both heavy metals and organic compounds at a time. So, we will continue with the nano adsorbents. So, in the next session, till then, thank you.